Hi all, this is Dennis and you on the Dan Electro channel. Today's video will be dedicated to this power supply. I'll show you how to change its voltage. The power of this power supply is 200 watt. At the output it produces a voltage of 5 volts, with a current of up to 40 amperes. But for many electronic devices, 5 volts is not enough. Therefore, I decided to make the power supply more universal. I will make sure that the voltage at the output of this power supply is adjustable. It will change from 3 to 21 volts. The entire alteration will consist of adding a variable resistor and changing the connection of the transformer windings. And now I'll explain to you how to do all this. Enjoy watching everyone. The power supply that I will remake looks like this. On one side it has a terminal block for connecting wires. The first 2 terminals are supplied with mains voltage. The third terminal is grounding. The last 6 terminals are the output from the power supply. 3 for plus and 3 for minus. To the right of the terminal block there is a trimmer resistor. With its help, the output voltage can be changed within small limits. On the side there is a sticker with the characteristics. 5 volts, 40 amps, power 200 watts. The power supply housing consists of 2 halves. One is made in the form of a grill for air convection. And the second one is made from a piece of aluminum. It adds strength to the case and acts as a cooling radiator. The inside of the power supply looks like this. There is a lot of free space. All the parts are located at a great distance from each other. It's immediately clear that the developers did not have the task of making the power supply more compact. The huge choke and transformer immediately catches your eye. For a 200 watt power supply, the transformer could have been taken smaller. But here they apparently played it safe and took a larger core so that thicker wires could be wound there. Thanks to this, they will heat up less. On the high voltage part of the circuit after the diode bridge there are 2 high capacity capacitors. Each is 470 microfarads and 200 volts. The capacitors are connected in series. The power supply is assembled using a push-pull half-bridge topology. Its operation is controlled by the TL494 chip. Next to it on the radiator there are 2 bipolar transistors. Using them, the TL494 microcircuit supplies current to the primary winding of the transformer. A transformer is installed in front of the transistors to drive these transistors. The current from the secondary winding of the transformer is rectified from both half cycles. So 2 diode assemblies are installed here, each for its own half cycle. They are also located on the radiator, but here it is much larger. The assemblies use Schottky diodes. Each of them is designed for a voltage of 45 volts and a current of 40 amperes. Next to the diodes is the ruler of all chokes. It consists of 2 rings and 2 windings. The ripples of the secondary winding of the transformer are smoothed out by 4 electrolytic capacitors. The capacity of each of them is 2200 microfarads, and the nominal voltage is 10 volts. The capacitors are connected in parallel. Their total capacity is 8800 microfarads. The entire power supply board is varnished on both sides. Most likely this was not done at the factory as everything looks very sloppy. As I already said, there is a variable resistor on the board. You can use it to change the voltage. But the problem is that it didn't work for me. Therefore, I had to remove it and solder another one. But before increasing the voltage at the output of the power supply, the capacitors on the low voltage side must be changed. As I already said, the capacitors at the output of the power supply are low voltage, only 10 volts. And therefore, to prevent them from exploding after the voltage increases, it is better to replace them with higher voltage ones. In addition, the resistor in the low voltage circuit must be changed. Its resistance is only 50 ohms, and therefore when the voltage increases, it will become very hot. I removed all the necessary capacitors from the board. Instead, I'll put one at 470 microfarads 50 volts. Although its capacity is small, it has a high operating voltage. In the process of remaking the power supply, you don't have to worry about it exploding. After I determine what maximum voltage this power supply can produce, the capacitor can be changed to the appropriate voltage and capacitance. Instead of a 50 ohm resistor, I'll set it to 270. Just in case, I'll take two cotton ones. The capacitor and resistor are placed on the board like this. I also replaced the variable resistor. The original resistor was 1 ohm. I set it to 47 ohm. Now you can turn on the power supply and see in what range the voltage changes. After turning it on, the voltage immediately appeared. The multimeter shows about 6 volts. As the resistance increases, the voltage begins to decrease. But even if you unscrew it all the way, the minimum voltage remains at 2.5 volts. Thus, I found out that the voltage range of this regulator is small, only from 2.5 to 6 volts. As you can see, the voltage did not change much using the factory adjustment. So to increase it even more, you need to find another way and study the power supply circuit. To make it easier for you to understand what I changed in the power supply, I drew a simplified diagram of it. Its low voltage part is shown here. Diodes, inductor, smoothing capacitors, resistor and signal LED with quenching resistor. And I think many people have a question. What is this resistor for? This is an ordinary shunt. Yes, this power supply has it. Overload protection is based on it. By the way, it looks like this, made of 4 jumpers. Now let's go back to the diagram. The variable resistor with which I changed the voltage is connected to the minus of the power supply. I will call it resistor R5. It doesn't matter how it's labeled on my power supply. After all, the numbering of resistors in your power supply may be different, so don't look at my designations. The main thing here is that you understand what part we are talking about and understand its function. After resistor R5 there is another 1 ohm resistor. This entire chain is connected to the first pin of the microcircuit. There are also a few more parts connected there. In my case, these are 2 resistors and a capacitor. A 1.2 kilo ohm resistor is connected to the positive side of the power supply. Thus, a voltage divider is obtained from resistors, connected to the first pin of the microcircuit. By changing the resistance of the divider arms, you can change its voltage at the center. The TL494 chip looks at this voltage and changes the voltage at the output of the power supply. Instead of a constant 1.2 kilo ohm resistor, I decided to use a variable one. I'll also take 47 kilo ohms and call it resistor R10. Further in the tests, resistor R5 will be turned to the minimum. Its resistance will be 0 ohm. To operate, the microcircuit receives power from another winding of the transformer. This is also a secondary winding. She has her own rectifier. In this diagram I have depicted the secondary windings as independent, but in reality they are connected. I'll talk about this a little later. I'll see what happens. Please note that this time I turn on the power supply through the safety light. Resistor R5 was factory adjusted. But now I am already making a significant change in the circuit and it is not clear how the power supply will behave. The power supply turned on. The multimeter shows approximately 5.5 volts. I rotate the variable resistor and reduce its resistance at the same time the voltage decreases. Now I increase the resistance and the voltage begins to rise. Using variable resistor R10, it was possible to increase the voltage from 5.8 volts to almost 11. Not bad. We doubled the power supply voltage from 5 to 10 volts. If this is enough for you, then you can leave it like that, but you can go further and increase the tension even more. To do this, you will have to delve into the windings of the transformer. Then I unsoldered the transformer, studied the output of the windings and rang them. There are a lot of conclusions and at first glance it seems that everything is very complicated. But in fact, if you are careful and know what to look for here, you can quickly figure it out. I will explain which winding each transformer terminal belongs to. The first, second and third terminals are the primary winding. The primary winding here is divided into two half windings. To increase the electromagnetic coupling between the primary and secondary windings, half of the primary winding is located inside the transformer, and the other is outside. Their connection is on the first pin, so the leg there is shortened. It does not fit into the board hole. The fourth leg of the transformer is missing. The secondary winding of the transformer also consists of two semi-windings. The secondary winding current is rectified from both half cycles, so the secondary winding has a middle terminal or, as it is also called, a midpoint. The connection of the secondary half windings is located at pins 5, 6, 7 and 8. On the board these pins are connected together. The 9th, 10th and 11th pins are the end of one half of the winding. 14, 15 and 16 pins are the end of the other half of the winding. In addition to the main secondary winding, which generates a voltage of 5 volts, this transformer has another secondary winding to power the microcircuit. It also consists of two half windings and has a midpoint. The middle point is on the 6th pin. The ends of these windings are located at pins 12 and 13. The wire in the power winding of the microcircuit is thin and presumably there are more turns there, since a voltage of more than 5 volts is required to power the microcircuit. The 5-volt winding is made of stranded wire. To increase the voltage on it, I will try to separate these wires. To separate the cores of the secondary winding, they must be heated and simultaneously untwisted. Unfortunately, it was not possible to do this accurately. With such thick vanes, this turned out to be very difficult. 3 legs on the frame broke off. Luckily, I won't need them. After entangling the secondary winding connections, I learned the following. Each part of the secondary winding consists of 2 bundles of wires. Each bundle has 4 cores. It turns out that one semi-winding consists of 8 cores. I will now test the transformer with a multimeter, and mark the beginnings and ends of these beams with lines on the screen. In the diagram, these bundles of wires will look something like this. As I already said, there are 2 bundles in each half winding. Each of them has 4 cores. This was the connection between the half windings before I disconnected them. After desoldering the transformer from the board and separating the half windings, it turned out like this. The bundles of wires are not connected to each other and I can connect them as I need. I will connect the ends of some bundles with the beginnings of others. Thus, each half of the half winding will become twice as long. And the voltage at the output of the power supply will also double. This is similar to connecting batteries in series. The more batteries, the higher the voltage. Then I connected the parts of the secondary winding as shown in the diagram. For a while I would solder wires to all the waters. The power supply must be checked with a new winding connection. The middle point of the secondary winding will remain here as before. To connect the half windings, I installed a small jumper. These jumpers will connect the ends and beginnings of the bundles. And these wires will be the ends of the secondary winding. During testing, tape must be placed under the transformer, otherwise the multimeter readings will be incorrect. I turn on the power supply and see what happens. Variable resistor R10 must be set to its minimum value before this. The power supply started working and still produces 3.5 volts as before. I slowly rotate the variable resistor and see what happens. Now the tension is rising even more. As I expected, from 10 volts the voltage doubled. Now the voltage at the output of the power supply can be changed from 3 to 21 volts. I also noticed that even with a slight rotation of the resistor, the voltage increases very strongly. When it reaches the maximum, the resistor still has free play. This suggests that the resistance of this resistor needs to be lower so that the voltage increases throughout the entire range of rotation of the regulator. Now that I have made sure that the power supply with the converted transformer is working properly, the transformer can be soldered back onto the board. I removed the temporary jumpers of the secondary winding. Instead, I soldered thick copper wire. I shortened these legs so that they would not fit into the holes on the board. The jumpers do not protrude, so the transformer should fit onto the board as before. But after trying to install the transformer, the problem still appeared. The new jumpers rest against these two diodes and a capacitor that were installed under the transformer. Now they will have to be unsoldered and soldered to the back of the board. Now nothing interferes with the transformer. The jumpers protrude beyond its boundaries, but do not touch anything. Here one of them is located next to the throttle. And here with a capacitor. No short circuit should occur. In both cases there is a gap between the parts and the wires. Now the power supply needs to be checked again. Everything works great. As I said earlier, the resistance of the variable resistor R10 turned out to be very large. To regulate the voltage more smoothly, you need to install another one. To find out what resistor value is needed, you need to do the following. By slowly rotating the variable resistor, you need to get to the point where the voltage stops increasing. Then you will need to unsolder the variable resistor and use a multimeter to measure the resistance that results from rotating the resistor. Since the voltage of the power supply has become 4 times higher, you need to think about what capacitors to replace the old ones with. Instead of the ones that were there, I will also put 4, but I will connect them differently. They will be arranged in this way, in series and in parallel. In this case, the capacity of the group will be 2 times less than the capacity of one capacitor from this group. Here the total capacitance will be 1100 UF, and here it will be 750. Each capacitor is designed for 16 volts. When connected in series, their voltage is summed. Thus the maximum voltage of each group will be approximately 32 volts. To make the capacitors charge more evenly, I added 2 resistors. The total capacitance of the capacitors will be 1850 microfarads. After soldering these capacitors, we got something like this. They are held on only by the wires, but do not dangle much. But then, just in case, I will glue them with hot glue. I left the 270 ohm resistor unchanged. I changed the variable resistor R10. Instead of 47 ohm, I took it to 10 kilo ohm. Now the voltage changes over the entire range of the variable resistor. I removed resistor R5 and put a jumper in its place. After remaking the power supply, I decided to do a little testing to connect an electronic load to it. First, I will load the power supply at a voltage of 10 volts. With a current of 16 amperes, the voltage dropped by 0.3 of a volt. Unfortunately, I can't load it anymore. This is the maximum current for my electronic load. If anyone is interested in how to make it, you can follow the link in the description. Electronic load of individual design, assembled on LM317 microcircuits. Now I set the voltage to 15 volts. The voltage dropped by 0.2 of a volt. The current was 15.2 amperes. The power supply produced 225 watts of power. This is 25 W more than stated. After watching this video, I think you understand the basic principles of how you can change the voltage of any power supply. For beginners, this may seem complicated, but in fact, upon closer examination, everything becomes clear. That's all for today. Put like, subscribe to my channel if you haven't already, ask questions in the comments if someone doesn't understand something. Click on the bell so you don't miss new videos, and bye everyone.